Okay, hello everyone. So we are starting a new topic today, which is refraction of light. What is refraction? This is actually bending of light. Like when light travels, we say that light rays travels in straight lines, straight path. But under certain circumstance, it can change the direction. It can bend from its original direction. So what are the reasons? When the speed changes, the velocity changes, when light goes from one medium to another medium, the speed can change. We know that speed of light depends on the medium it's traveling through. It travels at 3 times 10 to the 8 meters per second, the highest velocity, through free space, through vacuum, and much closer to this number, it travels through atmosphere as well, through air. Little slower than this, but very, very close. So this is the highest speed it travels, but if it travels through some other medium, like let's say glass or water or something, it slows down. Depending on this how dense the medium is, like how these molecules, how compact the molecules are, it slows down a little bit. So when the speed changes in that boundary, when it enters a different medium, when it goes from one medium to another, the direction can change. So it is something like this. Let's say there's some surface, like a piece of glass, right? Let's say it's a mirror. Now, if a light beam comes in with some incident angle, when it reflects, we know that it goes out like this, and we can draw this perpendicular line, which we call the normal. And in reflection, now this is reflection we are talking about. Reflection, we know that the two angles, theta I, the incident angle, theta R, the reflected angle, reflected, they are equal, right? It's a pretty simple relationship. Theta I equals theta R. At the same time, when it is reflecting, some of the light can enter the second medium. What is the second medium I'm talking about? Over here, air. This is the first medium, the medium the light originated, right? Let's say the medium 1. This side is medium 2, glass. Some of this light can enter the second medium. Now, this glass layer has a reflective backing. Imagine something like this. Just a piece of glass, a thick slab of glass. So here comes the incident light. This is the first medium. This is the second medium, which is glass, medium 2. On the surface, it can still reflect. It's a shiny surface, so it can reflect some amount of light, but some of this light can enter the second medium, can enter glass. Now we expect light to go in this direction, right? This is the direction it was coming in. So if you extend that, it's gonna look like this. But what really happens is it's gonna bend. At this boundary, at this surface, the boundary between the two mediums, it bends a little bit. That is called refraction. Now this light is refracted ray or refracted light. This is your theta I. This is the refracted angle over here. Theta refracted. Now why is it bending? Why the refraction happens? It's because it slows down, the speed changes. Okay, so let's talk a little bit more, get into a little bit more details about the speed changes. Now, it's a material property, it's a property of a material that, especially when it comes to optics, if light is able to travel through the material, like things like glass and air and water, they're transparent to light, right? They have something called the refractive index. Refractive index is defined as n is equals to speed of light in vacuum, which is this number over here. We normally represent that using letter C. Refractive index is equals to the speed of light in vacuum divided by speed of light in that medium. So we use the letter V. So for any given medium, let's say we want to find the refractive index of glass, we can say Ng, refractive index of glass, equals speed of light in vacuum, it's just C, it's a standard, divided by speed of light in that medium, so in glass, so that will be Vg. So if you know these velocities, now this we know 3 times 10 to the 8. If we know this velocity, what the speed of light in glass, for an example, let's say there is a particular glass, a particular type of a glass, the speed of light in that glass is, let's say, 2.3 times 10 to the 8 meters per second, right? So we know that it travels slower than this, so we have 2.3 times 10 to the 8, right? 10 to the 8. So let's see, what is Ng? What is the refractive index? 3 times 10 to the 8 divided by 2.3 times 10 to the 8 gives you 3 divided by 2.3, which is 1.304. 1304, approximately 1.3. Refractive index of this particular glass is 1.3. Refractive index doesn't have a unit, it's a ratio of two velocities, so it's just a number. Alright, so to the right you see this table. We have a couple of indices for different materials. You see that vacuum has a refractive index of 1, and it's obvious from the definition, right? N vacuum, speed of light in vacuum divided by speed of light in vacuum, right? You're dividing the same thing, right? This comes from the equation. This is 3 times 10 to the 8. You divide it by the same thing, comes to 1. Air has 1.0003. It's little slower than the vacuum, the speed inside air. So you can go back and use the equation to figure out what is that speed is. That will be a simple activity exercise to do. So let's try another example. Let me clear this. What is the speed of light in water? So let's use the equation. NW is equals to C over VW. Refractive index of water is equals to this number C divided by velocity of light in water. So from the table you can see that's 1.33. 3 times 10 to the 8 divided by VW. So VW is 3 times 10 to the 8 divided by 1.33, which is equals to 2.255 to the 8 meters per second, right? And you can see as the index increases, the speed of light decreases. In other words, when the medium is getting denser and denser, the speed decreases. So according to this table, diamond has the highest density, or so it slows down the most. Okay. Alright, so let's move on. Okay, so let's look at a ray diagram for refraction. Now, refraction is bending of light due to the speed change at the boundary when the medium changes. This bending can happen in a couple of different ways, and also the speed change. So think about a situation like this. Now here's a boundary. This is air. Let's say this is water. Imagine like a beam of light coming through air. So it's like you have a flashlight shining it into the surface of the water. So it's going to enter the second medium, enter water. All right. Now, whenever light comes in with an angle, whenever it has some non-zero incident angle, that means there is some angle, it bends. But if you shine the light straight down along the normal, like this, right? Put your light source over here. This is a light bulb. If we select a light beam that is perpendicular to the surface, in other words, one that comes along the normal, it just continues the straight same line, right? It won't bend. It will slow down. Some of it will reflect, will go back along the same path. Over here, it goes this way, but in this case, the perpendicular case, it goes back in the same path, and some of the light will enter the second medium. It will slow down. The speed will be different. Alright, so let's look at some ray diagrams. So here on this diagram you see, let me make it a little bigger. Here the light goes from air to water, and we have marked the refractive index of air as N1, the first medium, index of water as N2 because it's a second medium. So you see the incident ray, the reflected ray, the refracted ray, and you see the two angles. Theta 1 is the incident angle. Theta 2 is the refracted angle. Now here's the thing. If light enters a thicker medium, just 1 second. So what's the relationship between these two angles? Why do we have a smaller theta 2 in this case? What determines that? So here's the rule. If light enters from a thin medium to a denser medium, or a thinner medium to a thicker medium. Now, when you compare air versus water, you can see that the molecules they have a lot more space between them compared to water, which is tightly packed. Molecules are much closer. So in terms of optics, water is a much denser medium compared to air. So if the medium is denser, it has a high refractive index. So N water is much bigger than N air. So in our example, this is N water, which is this is air, which is our first medium, so we call it N1. This is water. This is our second medium, so we're going to call it N2, and we know that N2 is bigger than N1. If you go back to the table, this is 1.33, this is 1, so this is bigger. So when that happens, when light goes from a thin medium to a dense medium, right, thinner medium to a dense medium, denser medium, it bends towards the perpendicular line. Or in other words, the angle becomes smaller, right? Theta r will be smaller than theta I. When it goes from a thin medium to a denser medium, it bends towards the normal, making a smaller refracted angle. Now the second diagram, that's the opposite. Here the light source is underwater. So incident light theta I or theta 1 is underwater, and light enters a thinner medium, which is air. So in this case, it goes from a denser medium to a thinner medium, and then the refracted angle theta 2 gets bigger. Theta 1 is this is our incident light, theta 1, incident angle. Theta 2, the refracted angle, is bigger than that. And also you can see the reflected light as well. If you measure the angle reflected angle, that will be equal to theta 1. In reflection, the angles are equal. Refraction, there's a difference. Angles could be bigger, smaller, depending on the density of the medium. The next slide, we'll see how to connect these two angles, okay? So here we see a conceptual example. This refraction, actually, we explain it, this relationship between angles, using something called the Snell's law. So we'll talk about that in a minute. Refraction is what makes objects half submerged in water look odd. Okay, so the person is looking at the bottom of the feet of this person who's standing in water. So looking at means the light from here, from the bottom of the feet coming in, it bends away from the normal. Now imagine there is an imaginary perpendicular line. It bends away from it, making a bigger angle, goes to this standing person on the ground, and what his eye does is, how the brain understands this is, it feels like, it's always follow the straight line, it feels like light coming from here. So let me draw a diagram to explain this a little bit more. Let me try to draw the person. Here's the land, and here's water. Here's the lady standing. Okay, it's raising hand. Here comes light. And it bends away from it. So this is the incident angle. This is air. This is water. So makes a big angle like this. It was supposed to go this way, but that didn't happen. So I'm gonna undo that. It goes in this direction, and we need to place this guy's eye right here. Oops, this is eye. Okay, so it goes to his eyes, but the way we understand, where the brain understands this is, it appears like coming from here. That means, so let's say this is person's leg. The leg appears over here. It's a weird diagram. So ultimately, it looks like this lady is shorter than normal, right? Because the legs appears a little shorter. Alright, okay, moving on. I know my diagrams are not the best. Okay, so how do we connect the two angles? So let me go back and draw this diagram. N1, in this case, let's say air. Here comes incident light. This is your theta 1, the incident angle, the angle in the first medium. Bends, theta 2, refracted angle. This is your second medium, N2, which is water. Snell's law says you can connect the two angles according to this relationship. N1, refractive index of the first medium sine theta 1, angle of the first medium equals to n2 sine theta 2. This is called Snell's law. So let's try an example. Let's say we have let's say light enters from air to water. From air to water. Incident angle theta I, when light enters from air to water, the incident angle is, let's say, 60 degrees. What is the refracted angle? So we just put R here, reflected also we put R. So just keep in mind I'm asking the refracted angle. What is the refracted angle? So let's draw a diagram. Let's draw a new diagram. This is air to water boundary. Here comes incident light making 60 degrees. This is your theta 1. This is your N1. This is your N2. Always the medium where light originates, we take it as the first medium. So N1, and also the angle is theta 1. Now because water is denser, it's going to bend towards the normal, making a small angle, which is theta 2. This is what we need to find out. So let's plug everything into the equation. N1 sine theta 1 equals N2 sine theta 2. N1, index of air, just 1, sine 60. N2, index of water, 1.33 from the table, sine theta 2. So what is sine theta 2? Find that using the calculator, and then you can find what theta 2 is. So sine 60 by 1.33, I have sine theta 2 equals 0.6511. Therefore theta 2 equals 40.62 degrees, smaller than the incident angle, smaller than 60 degrees. So this is how we find the refracted angle, or if you want to, incident angle, whatever you need. Okay, all right. Okay, let's try another example. This time, let's say here's a swimming pool. There's the surface of the water. This is the bottom of the swimming pool. There's the shore. I mean, outside somebody standing. There is a person swimming underwater, and he's shining a flashlight. Okay. So question is, if the incident angle is theta equals 30, what is theta 2 refracted angle? Right? This is water, this is air. So the diagram should look like this. Here comes the incident. Oops. Here comes the incident light making 30 degrees. It's going to bend away, going like this. What is this angle? Theta 2. Same thing. N1 sine theta 1 equals N2 sine theta 2. Now your N1 is water in this case, right? That's the medium where light originated. So that will be 1.33 sine 30. N2 is air sine theta 2. So this gives us sine theta 2 is 1.33 divided by 2. I mean 1.33 sine 30. Sine 30 is half. Which is 0.665. So theta 2 I get 41.6, 41.7. That's the refracted angle. Okay. All right. Here's an exercise for you. Refraction through flat glass. Light traveling in air strikes a flat piece of uniformly thick glass at an incident angle of 60. You see that light coming in over here, making a 60-degree incident angle, and it bends with this theta A making a smaller angle. Index of refraction of glass is 1.5. So glass has n equals 1.5. What is the angle of refraction theta A? So this first angle over here. What is the angle theta B which the ray comes out? Now it bends, it strikes the second surface and it comes out. Right? So think about it. How to find this angle? There's some geometry you're going to use. And important information is it's a uniformly thick glass. Uniformly thick means this thickness does not change. Means the two sides are parallel. That is important. Okay? Alright. Give it a try.